Yeah, welcome everyone. Today we have Konstantin Tikhomirov from CMU, and he's gonna talk about the recent nice result of his on the Ramsey numbers of hypercubes.
Thank you very much. Thank you for the invitation. I must say that I am definitely not an expert in extremal combinatorics and have been learning this subject in past 2-3 months. So I just want to warn everyone in advance that my vision of this subject may be not correct in a sense. So my perspective may be not correct because simply because I don't know the literature yet. So nevertheless, I want to try to give some perspective to this work, the way I see it. I was interested in this question not because hypercube is such an important graph to understand its Ramsey number, but rather to try to understand what the general principle is in regard to Ramsey numbers of sparse graphs. So hypercube is a reasonably sparse graph, and you can say what is the property that guarantees that the Ramsey number is relatively large versus not that large. So I'm going to make this a bit more precise. So in this talk, let me talk about bipartite graphs only. I will not discuss more. Okay. Okay, so so what is known about bipartite graphs in general? So suppose that we have bipartite graph H, say on n vertices and of maximum degree D. So what is known about the Ramsey number? And for me, the Ramsey number really is a way to characterize embeddability properties of the graph, how easy it is to embed the graph. And in fact, very often, at least for bipartite graphs, bounding Ramsey number from above proceeds just by showing that if you have an ambient bipartite graph of density at least 1/2 on that many vertices, then you can embed H into that graph regardless of the structure of the edges. So you just need the density to be sufficient. So there is an upper bound. Ramsey number of H is less than, or I can just write this with big O notation. So, and here I should put, let's see, 2 to the D times N. Okay, so in this form, the result is due to Conlon, Fox, and Sudakov. And it proceeds by employing the dependent random choice. I'm going to talk about that in a moment. What about the lower bound? Well, the trivial lower bound is n, of course. It is also known that for graphs with strong enough expansion properties, a lower bound of the type n times some exponent of d also works. So let's just want to make sure that I spell the names of the authors correctly. Yeah, so this is the result of Graham, Rödl, and Rusinski. That if H has strong enough expansion properties, then the Ramsey number of H is bounded from below by n times 2 to the CED, and C is some universal constant. Here I must say that in their paper, as far as I remember, they proved this result for random result of this type by considering a random graph, not bipartite, but their argument can be adapted to the bipartite setting. So what it means, strong enough expansion properties, it is really not clear. In their proof, what they need is whenever you consider a decomposition of the vertex set of the graph into exponentially many in D subsets, into 2 to the C prime D subsets, say, for some constant C prime, which is in a certain way related to this constant C. So they require that for a large proportion of the pairs of the subsets, they will be well connected. So random graphs, at least some models have been checked, satisfy this property. But in principle, deterministic graphs satisfying similar properties can also be constructed. So the question that can be asked in this context is what really influences the magnitude of the Ramsey number of bipartite graph of, say, maximum degree D. So in principle, we can expect anything from n when we consider some trivial graphs with really no structure to n times some exponent of D, and this is definitely known when the graph has strong enough expansion properties. So what really influences the magnitude of the Ramsey number of H? So in here, what I want to propose is definitely have been noted in the literature in a non-rigorous form, just the way I'm presenting it here. That so if we have appropriate expansion properties, then we should expect at least n times an exponent of D. And if we have no expansion, then we should expect something just maybe a little bit bigger than n. I can write it like n times 2 to the little of D. So what it means, appropriate expansion properties and no expansion, of course, is not clear. So it seems to be quite interesting to understand what we can put in here as some specific description of the structure of a graph, rather than these vague terms. So the conjecture of Burr and Erdős is that the hypercube is of the second category, no expansion in that sense. So the conjecture is that if we have the hypercube on 2 to the n vertices, so minus 1, 1 to the n, its Ramsey number should be of order big O of 2 to the n. Okay, and there have been some work on that problem, as well as on more general questions that sort of comprise this problem as some specific instance. So after several successive improvements, the best known upper bound on the Ramsey number of the hypercube was this. So we go of 2 to the 2n, and you see this is just this result of Conlon, Fox, and Sudakov applied to the cube. So I should mention their paper here. But also I should mention the paper of Lee, where he resolved that famous conjecture about Ramsey number of D-degenerate graphs. And his argument also gives the upper bound of this form, but with better constant than in the paper of Conlon, Fox, and Sudakov. So next part of my talk, I want to describe the dependent random choice and some limitations of the method, at least in its sort of in its simplest version. So, dependent random choice. So, how we can show a bound of this type? Or I will consider something a bit weaker, actually. So, in the form that I'm going to discuss, the technique, it will be possible to give an upper bound of the form 2 to the 2n plus little of n on the Ramsey number of the hypercube. But it still will give a quite good illustration of how the existing proofs proceed, more or less, at least at the high level. So dependent random choice can be viewed as a two-step procedure. So first of all, I want to consider bipartite graph in this shape. So we have two parts arranged like this. So it will be V up and V down. So all bipartite graphs will look like this in my talk. So suppose that we have a graph H. So this is a graph whose Ramsey number we want to estimate. Let's assume that the graph has, say, m plus m vertices. I will not consider a most general case, so let's assume that it's balanced in the sense that two parts have the same size. And say maximum degree d. So how this estimate proceeds? So we need an ambient graph, a graph of density at least 1/2, bipartite, into which H is going to be embedded. So let's denote it by capital G. So this is bipartite graph. Of edge density at least 1/2. Okay. So the idea is to first choose in a special way a subset of V up. So first choose a subset. Step 1. Choose subset S of V up G, which has at least M elements. So with least M vertices, such that if we consider a uniform random D-tuple of vertices from S, then with very large probability, the number of common neighbors of these D vertices is going to be at least M, such that with very high probability, uniform random D-tuple of vertices, I'm going to name it V1 to Vd in S, has at least M common neighbors in the other part of the graph G. And then the next step is embed V up H, so the M upper vertices of the graph H into the subset S uniformly at random. Okay, so here, let's see, very high probability. So what the probability should be? If the probability is at least 1 minus little o of 1 over M, that's enough. If probability is that high, then when we embed the upper half of the vertex set of H into S, with positive probability, we get the situation when every D-tuple that corresponds to a set of neighbors for a vertex in VH down will have at least M common neighbors in the graph G. So what this means, we can use some iterative embedding procedure to sort of complete the embedding. So far we have just the set V up. So to embed VH down, we can proceed one vertex at a time. So we pick arbitrary vertex from this vertex set, and then we embed it in such a way that its image falls into the set of common neighbors of the corresponding D-tuple from the set S. So this will work just because the set of common neighbors for every D-tuple of interest for us is at least M. So we will never encounter a situation when sort of the set of admissible vertices is exhausted. So this completes the embedding. I did not describe the way the set S is constructed. Now, it is done using first moment argument. Maybe I will discuss this a little bit in a few minutes. But what is important in this procedure is that two remarks. So first, remark one. This procedure is sufficient to show that, let me write it in for the hypercube specifically, that the Ramsey number of the hypercube is of order 2 to the 2n plus little of n. So this can be proved using this argument. And remark two, this scheme cannot be used to show that the Ramsey number of the hypercube is less than 2 to the 2n minus epsilon n for any constant epsilon bigger than 0. So this scheme just breaks for specific graph G. It cannot produce a good embedding via this process, no matter how the set S is constructed. That's very interesting. So maybe it may be of interest to try to augment the usual process of the selection for the set S, this first moment method, from the base version of the dependent random choice to something more advanced, and hope that this will fix the situation, or at least will lead to some further progress. Unfortunately not. So there is an example of the graph. I have this example in the preprint. So I will not prove anything about this example, but I still want to mention how to construct it. So I want to construct a graph G such that hypercube cannot be embedded into the graph G via this two-step procedure. Okay. So more specifically, for every epsilon bigger than 0 and n greater than n epsilon, there exists a bipartite graph G on 2 to the 2n minus epsilon n plus 2 to the 2n minus epsilon n vertices. So we plunge just a little bit below the threshold, 2 to the 2n threshold of density 1/2, such that the hypercube cannot be embedded into G via the above procedure. And the way this graph is constructed, it has some sort of block structure. So the idea is this. So we have this set of the vertices V down G, which is split into blocks. So the number of blocks should be chosen carefully. Then the idea is for every vertex here, we choose uniformly at random half of the blocks. Okay. So for example, here we have 8 blocks. So we need to choose uniformly at random 4 blocks. Then for each of the chosen blocks, we connect this vertex to all vertices in the block, like this. So we will have a picture like this. Suppose that we choose these four. Then this is how the connection will look. Then we choose the second vertex here and perform the same construction independently from the first one and so on. So we do this for every vertex in the upper half of the vertex set. And then it can be shown that with high probability, this graph has the following properties. So if you choose a set S here of size, say, for the 2 to the n, size necessary to embed the upper half of the hypercube, well, it should be 2 to the n minus 1, doesn't really matter here. Then no matter how this set is chosen, for most n tuples of vertices from the set S, their set of common neighbors will be confined within a subset T of the lower half. Subset T of size much less than 2 to the n minus 1. 2 to the n minus 1, yes. So what this means? So it means that if we try to embed the hypercube at the second step here, we will encounter a problem because when we try to embed the lower half iteratively, one vertex at a time, inevitably at some point we will encounter a situation when there are no free vertices available. They have been chosen at previous steps already. Yes, because all common neighbors sort of are confined within a very small set, much smaller than the cardinality of the vertex set for the hypercube. So without some substantial fixes, this method cannot improve existing estimates on the Ramsey number. Okay. So please let me know if there are any questions at this point before I turn to the second part of the talk.
Are you saying that there exists such a set S, or are you saying that
no, for every set S of this size, it has the property that most of n tuples of vertices within this set have the set of common neighborhoods, set of common neighbors, which is mapped into some set T. T here is a function of S, right? T should be viewed as a function of S. But the point is, for any set S in the upper half, the vertex set of this cardinality, there exists T much smaller than 2 to the n minus 1, such that essentially all common neighborhoods are confined within T. So no embedding is possible.
Okay, thank you.
Okay, so in the second part of the talk, I'm going to actually discuss the proof ideas. So what can be done here, what can be fixed with this method. Still want to use dependent random choice. So first I want to state the theorem. The Ramsey number of the hypercube is the whole of 2 to the 2n minus cn for a universal constant c bigger than 0. So if my computations are correct, and this is the first draft and I may have made some mistakes, so my computations give c can be chosen of this order. So not a big improvement really, assuming that n is sufficiently large. assuming that n is sufficiently large, we can remove this big O, just write less than or equal to 2 to the 2n minus cn. So the important thing here is therefore not the sort of quantitative improvement itself, which is still very far from the conjecture, but some additions to the dependent random choice techniques. So what can be done to fix the scheme that I presented before? So let's see what is the problem of this scheme. So the problem is here. So in this example, so we have a subset S. No matter how we choose it, we take n tuple, take the common neighbors of these n vertices in the lower half, and they all turned out to be, or almost all, within the set T. So it means that the set of common neighbors is sort of concentrated. There is some notion of concentration for the set of common neighbors. If they were not concentrated, if they were spread, so imagine that we managed to find a set S such that set of common neighbors of a typical n tuple, it still will probably have the size of order 2 to the minus n times the cardinality of V down G. So this is something that is reasonable to expect, right? Density of the graph G that we will be working with is 1/2. And so if we sort of assume that the set of neighbors for a vertex for vertices from the set S are sort of in general position, so more or less behave like random subsets of V down G, then the intersection of n such subsets should produce a set of size roughly 2 to the minus n times V down G. So if this set by our construction has cardinality 2 to the 2n minus cn, then we have additional 2 to the minus n. The set of common neighbors for a typical n tuple of vertices in S will have size 2 to the n minus cn, much smaller than the size of the vertex set of the hypercube. Regardless of that, if we know that these sets of common neighbors are spread across the set V down G, this won't be a problem. We will still be able to fit the lower part of the hypercube in such a way that in our iterative embedding process, we will never run into the situation when all available vertices are already extracted, have been chosen at previous steps. So the idea, if the sets, and here I'm going to use a notation, the set of common neighbors, I will be denoting like this. This is a set of common neighbors in the graph G of V1, V2, Vn. So we have these sets where the vertices V1, V2, Vn are just n tuples of vertices in S. So I should just consider the Cartesian product, say. Whether they repeat or not repeated, that's really not important technical detail here. So if these sets are sufficiently spread, in V down G, then the above scheme can be fixed. So it will work. assuming a careful embedding process for the lower half of the vertices of the hypercube. So in this case, we're good. The problem is that this case is not always the case. In this example, the problem exactly that the set of common neighbors are not spread. They sort of hit the same point again and again, no matter which n-tuple of vertices from S we choose. So what can we do in this case? So let's first consider the extreme situation when the set of common neighbors for every n-tuple of S is actually the same set. It's not just that they overlap and have huge overlaps. Assume that it's just the same set. So imagine that we have a subset S in the upper half. And now, no matter which n-tuple we choose, the set of common neighbors, this n-tuple, is going to be the same set T. So what it means? It means that of these 4 vertices, each vertex is connected to every vertex in T. So we'll have sort of complete bipartite graph here, bipartite subgraph. Since it's true for every n-tuple in S, it is true for every vertex in S. So we'll have just complete bipartite subgraph on the set S union T. So we'll get complete subgraph here. So what can we do with this subgraph? So let's just fix this picture and remove this subgraph from G. We just remember that this subgraph exists. This subgraph within G exists. And now let's remove it from G. So what we'll have next? So then we repeat the process. When we remove such subgraph from G, because both sets, S and T, in fact, the set S will have size approximately, or at least proportional to the size of the vertex set of G. The set S is big. Set T is small, it's exponentially small. So when we remove this subgraph, even though it's complete, we really remove very tiny proportion of the edges of G. There are still a lot of edges, and its density is essentially 1/2 still. So then it is we repeat the process, and one of 2 things happen. Either we're now able somehow to find the set S. Maybe at the very beginning we just didn't choose the correct set. So now, after we removed this subgraph and we restart our selection process for the set S for the new graph, denoted G1. So it's graph obtained from G by removing this subgraph. So now we run the procedure on the graph G1. And one of 2 things happen. Either we find now a set S in the graph G1 such that the common neighbors of n-tuples are spread, and then embedding would work. Or we have the same situation as here. If we have the same situation as here, we get a second bipartite. We have a second bipartite subgraph like this. So then we continue the process. So one thing I didn't make precise, but this is very important. So what I said is that G1 is obtained from G by removing this subgraph. In fact, something else happens. So in fact, G1 is obtained from G by removing, let me be more careful here, by removing edges incident to T, to the subset T. It means that I don't remove the vertices. So if I remove edges incident to the subset T, then I make these vertices isolated in G1 and they are useless. So I can also remove them. They don't matter anymore. But I do not remove vertices from the set S. And this is important because the set S in the proof actually has size roughly of order 1/4 of the size of the upper half of the graph G. So if I removed this number of vertices, I would be able to make only 4 steps at most in this process. But in fact, I make exponentially many steps. So eventually, what happens? Eventually, this bad situation that we described not very imprecisely so far, the bad situation when the set of common neighbors is essentially the same set for all n tuples in the set S, when it repeated in graph G, then on graph G1, then on graph G2 that is obtained at the next step, and so on, what we will eventually obtain is some sort of blocks. So we will be able to extract some kind of block structure from the graph G. So these blocks will look like this. So here I have the upper half and the lower half. The lower half of the vertex set will be split into disjoint subsets. Maybe not of the lower half of the vertex set will be used. Maybe some of it will be unused, but some considerable proportion is going to be employed here. So we'll have these blocks. So for every block, we will have a complete bipartite graph in this illustrative description. In fact, it's not going to be complete, but it will have density close to 1. Connecting this block to a set of size proportional to the size of the upper set of the graph G. So we'll have some complete graph, say, or almost complete graph on this union. Then for the second block, we will have complete graph on the union with some other set, say this one. So we have complete graph connecting this block with this block. So you see the blocks in the upper half intersect. Blocks in the lower half are disjoint. So this process goes on. So eventually what happens? Eventually we come up with a graph or a subgraph. We can extract from G a subgraph that looks very similar to the example that I discussed at the very beginning. This is a randomized example that actually produces the obstacle or illustrates the obstacle in extending the dependent random choice method. So what turns out is that it's not just an illustration, this randomized graph. In a sense, this is the only abstraction to the method. At least if we want an improvement by a small constant in the exponent. So, okay, so we have a dichotomy. Either the dependent random choice, the classical version, will work, maybe with some little adjustment on how to embed this lower half of the vertex set of the hypercube, or we can extract a block structure of this type. Suppose that we can extract the block structures, and what do we do with it? And at this stage, what is important is the structure of the hypercube. It is really important now that the hypercube is not just arbitrary and regular bipartite graph. It is important that the hypercube has very weak expansion properties. So specifically, what is going to happen here is that we're going to embed the hypercube into the graph, into the block graph G of this type, facet-wise. So here is the illustration that I'm using in the paper. So assume that we want to embed hypercube, just three-dimensional. So we can consider the partition of this cube into two blocks. So let's partition it into two blocks. So this one and this one. So according to the facets. So then within each facet, we have two vertices, which we regard as vertices from the, say, from the upper half of the partition of the hypercube vertices into two parts. So I will draw them in black. Okay, so these four vertices colored black, I want to embed into the upper part of G. And the remaining four blue vertices, I'm going to embed into the lower part of G. So, okay, let's see. So imagine that I'm embedding the facet, the upper facet, in the first block. So I'm embedding the upper facet, this one, into the first block, and the lower facet into the second block. So more precisely, I need to embed the two blue vertices here and two blue vertices here. Okay. So now the idea is the following. Look at any of the four black vertices. So what we can say about them? So of course, just because it's a partition of bipartite graph, of course, any black vertex is incident only to blue vertices. That's what it should be. But more importantly is where these blue vertices incident to the given vertex are located, in the same facet or in a different facet. And here we see the pattern. So say, take this black vertex. It has three neighbors. So 1, 2, 3. Of these three neighbors, two neighbors are in the same facet, and only one neighbor, two, in the opposite facet. So if we rescale these to higher dimensions, where this becomes more important, what we'll see is that for assuming that we partition the hypercube correctly, for any vertex from the upper half of the hypercube, most of the incident vertices will belong to the same, say, W facet. It shouldn't be n-1 facet, it will be some other dimension correctly chosen. So most of the neighbors going to be from the same facet, and only few neighbors from different facets. So now imagine that we want to put these vertices 1 and 3 in this block, and then embed this black vertex, I call it A. I embedded somewhere in the block corresponding to this one here. In the block which forms together with this one almost complete bipartite graph. Since this graph has huge density, there will be no problem identifying edges that connect the vertex A, or more precisely the image of the vertex A, to the images of the vertices 1 and 3. But we also have vertex 2, which is in the other block here. And unfortunately, about this vertex and its relation to the vertex A, we can't say anything. It belongs to a different block. So here we will be able to use some randomized argument to say that that sort of the density of the graph of the subgraph of G on the first block in the upper half of the vertices and this second block in the lower half is not too small. What it means not too small? Well, bounded from below by some universal constant, say 1/10, at least 1/10. Not that good. Not 1/2 definitely, less than 1/2. At least what we can guarantee, something less than 1/2. But the point is that the number of neighbors that are number of neighbors of A, which are in these unfortunate blocks, in these inconvenient blocks, is very small. Most of the neighbors of A, because they belong to the same facet, they are going to belong to the block which by our construction has almost density 1 here. The edge density is almost 1. So to summarize, the idea is once we extract the block structure from the graph G, is to split the hypercube into facets, not n-1 facets, but facets of appropriate dimension, and then embed hypercube, somehow preserving the facet structure. This, together with some further modification of the dependent random choice, which will be needed in this construction as well, to guarantee, say, that there is some connection between A and vertex A and vertex 2, that we can choose vertex A and vertex 2 in such a way that they are connected. Some kind of dependent random choice is needed, also based on the first moment method. But still, it will be possible to reuse this block structure to embed the hypercube more economically than the classical dependent random choice allows. That's how the dichotomy works. One technical element, in fact, in the paper, there are 3 alternatives. So I had to add a third alternative to sort of avoid some technical complications in this analysis process. So the third alternative just says that graph G contains a large subgraph of density considerably bigger than 1/2. In which case, again, standard dependent random choice would work just because we win on the density. If graph G does not contain this large subgraph of high density, which means that the edges are sort of more or less uniformly scattered between the vertices of the upper and lower half, then we will have the dichotomy within that situation, that case. Either spread common neighbors and then standard dependent random choice, or condensated common neighbors and then the block structure and then block embedding of the hypercube. So you see, when constructing proofs of that type, dichotomies or doesn't matter how many cases, it is hard to expect that such method will be able to give an optimal bound. I feel that there are some ways to improve the constant from 0.03 to something a bit more reasonable by optimizing some parts of the argument. At the same time, this method, I definitely do not think that this method can give conjecture of Burr and Erdős, or even sort of asymptotic version of the conjecture when you want to prove that the Ramsey number of hypercube is of order 2 to the n plus little of n. So this still out of reach. It is not clear if any ideas of this type can really lead to resolution of the conjecture. At the same time, some kind of the block structure of the hypercube is something that really is important to use. It must be used simply because we know that expanders and regular expanders have a Ramsey number much larger than the Burr and Erdős conjecture of hypercube asserts. But whether the block structure should be used in a fashion similar to this paper, or it should be something completely different, it's really hard to say. So I would like to stop here. Thank you very much.